The history of Earth is the history of rebirth, a planet that has died many times and yet always found a way to begin again. Beneath the apparent calm of blue oceans and green forests lies an invisible record, layers of rocks, ashes, and fossils that speak of eras of fire, ice, and silence. Earth has never been static. It pulses, breathes, and changes on timescales the human mind can barely conceive. Every mountain that now rises was once the bottom of a sea. Every desert was once a fertile bed where life thrived. What we call stability is nothing more than the pause between two collapses. Over billions of years, this world has been a laboratory of extremes. There were times when heat melted continents and others when cold froze entire oceans. Life, stubborn and adaptable, endured all these contrasts, leaving deep scars along its journey. Behind every forest, every living being that breathes, there is a lineage that survived the impossible. Nothing on Earth is new, and nothing is permanent. Everything that exists today is the outcome of countless previous deaths, of ecosystems that perished and made way for new ones, of species that vanished and opened space for others more capable or more fortunate. In certain eras, destruction did not come slowly. It was sudden, brutal, and absolute. Giant meteors fell from the sky, seas evaporated, volcanoes cloaked the planet in ash for thousands of years. In those times, balance was shattered so violently that life hung by a thread. Yet beneath the rocks, in the deepest waters, and in the darkest regions, something persisted. Tiny microorganisms and simple life forms were the seeds that, after each catastrophe, bloomed again. That is how Earth restarts, from almost nothing. What makes this planet so unique is not just the presence of life, but its ability to rebuild itself after every end. In a universe where destruction is the rule, Earth stands out as a resilient world. Scientists call this planetary homeostasis, the ability to maintain a certain balance even after great disruptions. But this balance comes at a price. Every time the planet is shaken, something is lost forever. Entire species, entire lineages disappear without leaving heirs. Earth survives, but it is never the same again. Geologists study the records of these transformations in layers of rock. Each one is like a page in a vast book, where we can read not only what lived, but also what died. Some layers are marked by volcanic ashes, others stained with oxidized iron, still others containing carbonized fossils, traces of catastrophes that wiped out almost the entire biosphere. Through these clues, we discover that life on Earth did not evolve in a straight line, but in leaps. Long periods of calm were always interrupted by catastrophic events that redefined everything that existed. These episodes, known as mass extinctions, are rare on a geological scale but devastating in impact. In each of them, more than 70% of species vanished. Diversity shrank, the world fell silent, and the very concept of life was put to the test. It was in these moments that the planet died, not literally, but as a metaphor for the near annihilation of the biosphere. And paradoxically, it was from these deaths that new cycles arose. Destruction opened space for biological innovations, for the emergence of new species, for evolutionary paths that would never have occurred without the previous collapse. When we observe the fossil record, we see an almost poetic pattern. Every great extinction is followed by a sudden blossoming of life. It is as if the planet needed to erase what once was to write a new story. After ice, warm seas appear. After ashes, forests are reborn. After silence, the song of life returns, different, adapted, stronger. This alternation between destruction and creation is not a flaw. It is the very essence of terrestrial existence. In the next few hours, we will travel through these eras of death and rebirth. We will walk across dried seas, forests turned to coal, and deserts where impossible creatures once swam. We will understand how each catastrophe was not the end of life, but the beginning of a new phase. Earth, after all, is a planet that never stops changing. And perhaps the greatest secret of its survival lies precisely in this, in dying just enough to live again. For the true story of this world is not that of life that blooms, but of life that endures. And it is this silent endurance that has brought us here. Before dying and being reborn so many times, Earth first had to learn what it meant to live. In its first billions of years, this planet was nothing like the blue and green world we know. It was a realm of fire and molten rock, covered by endless storms and skies suffocated by toxic gases. The surface boiled, the oceans were acidic, and the air contained no breathable oxygen. Yet amid the chaos, something began to happen. A series of chemical reactions, so simple and so improbable that they ended up producing the greatest miracle in cosmic history, the birth of life. In the primordial seas, rich in minerals, heat, and electrical discharges, molecules began to combine into increasingly complex chains. There, where light barely reached and energy was abundant, the first structures capable of replicating themselves emerged. They were simple organisms, invisible to the naked eye but endowed with a property that would change everything: the ability to copy themselves with small variations. It was the beginning of natural selection, a process that, without any awareness, would shape all future biological diversity. From these microscopic forms, the planet began to transform, slowly and silently. The first microbial colonies spread through the seas, consuming and releasing gases, altering the chemical composition of their surroundings. Among them appeared cyanobacteria, tiny beings capable of something revolutionary: photosynthesis. They learned to capture the energy of the sun and transform it into food, releasing oxygen as a byproduct. It was the start of an unprecedented planetary transformation. For millions of years, these microorganisms filled the atmosphere with oxygen, creating the conditions for new forms of life, and at the same time, triggering Earth's first biological collapse. Oxygen, which we now associate with life, was once a poison. For most primitive forms, it was lethal. Cells that thrived in oxygen-free environments began to die, suffocated by the new chemistry of the air. The oceans turned toxic, and their surface layers were devastated. Earth experienced its first great extinction, a paradox in which life itself destroyed the conditions that sustained it. The survivors were those that adapted to the new element, or found refuge in the depths, far from light and air. Over time, the concentration of oxygen stabilized and a new balance emerged. This gas, now abundant, reacted with minerals, rocks, and metals, transforming the entire planet. The iron in the oceans oxidized, forming red layers still visible in ancient rocks, a mineral testimony to a biological event. From that point onward, the atmosphere became breathable, and the sky finally turned blue. Out of destruction, life built a new world. The planet's response was immediate. The rise of oxygen triggered intense climatic changes. Temperatures dropped, and a succession of ice ages swept across Earth. For the first time, the planet entered a global freeze, what scientists call snowball Earth. Entire oceans solidified, and sunlight reflected by ice maintained the cold for millions of years. Yet, deep below, near hydrothermal vents and volcanic fissures, life endured. Extremophile bacteria and archaea, organisms capable of surviving the impossible, kept the flame of existence alive. This extreme period, which could have marked the end, was in fact a catalyst. When the ice began to melt, the planet re-emerged transformed. The oceans released trapped nutrients, and photosynthesis flourished once again. The atmosphere, once thin and unstable, became more balanced. It was in this renewed environment that life began to experiment with more complex forms, evolving from single-celled to multicellular organisms. This transition was slow, but it marked the beginning of true biological diversity. For the first time, there were bodies made up of millions of cells working together, a strategy that allowed new functions, movements, and structures to emerge. As life expanded, the planet continued to respond. The rise of larger organisms increased the production of waste, altering ocean chemistry. Primitive algae and sponges created oxygenated zones that spread across the seafloor. Meanwhile, the Earth's crust began to move more intensely. Tectonic plates reorganized continents and opened new seas. Geology and biology began to dance together. Every movement of the rocks changed the climate, and life adapted in response to survive. This cycle of action and reaction between planet and organisms became Earth's signature. Life became a geological force as powerful as volcanoes and storms. It shaped the planet, even as it was shaped by it. The soil, the mountains, the atmosphere, all began to bear the signature of living things. And for the first time, Earth became a truly integrated system, a world where biology and physics intertwined in a delicate balance. Around 800 million years ago, this interaction reached a critical point. The climatic changes caused by biological activity created an unstable but fertile environment. The seas became laboratories of accelerated evolution. New forms of life appeared, creatures with symmetry, tissues, and independent movement. Small animals began to crawl along the seafloor, feeding on sediments and bacteria. It was the prelude to an unprecedented biological explosion that would transform the planet and begin a new chapter of existence. Earth was learning to live, and soon it would also learn to die, because every creation on this planet is accompanied by an equivalent destruction. And life, from the very beginning, has been only a response to the instability of the world that shelters it. For hundreds of millions of years, life had flourished in the shallow seas. The planet was a mosaic of islands and archipelagos, surrounded by warm oceans, rich in nutrients and inhabited by fascinating creatures. Trilobites, brachiopods, primitive corals, and calcified algae formed exuberant ecosystems, like submerged gardens, where diversity grew at a rapid pace. The atmosphere became increasingly stable, and the sun lit a world that seemed to be finding its balance. But Earth, as always, never stayed quiet for long. Something deep began to change in the planet's interior. The tectonic plates, in constant motion, slowly pushed the continents toward the South Pole. Mountains began to rise, and the global climate entered a silent transformation. Carbon dioxide, once abundant, started to be removed from the atmosphere as the new rocks absorbed the gas through weathering processes. This detail, seemingly harmless, was the fuse for a planetary catastrophe. With less carbon dioxide in the air, the greenhouse effect weakened and heat began to escape into space. Cold descended upon the planet with the slowness of a curse. First came the polar winds, then the glaciers. In a few hundreds of thousands of years, a blink of an eye on the geological scale, enormous ice sheets covered the supercontinent Gondwana. Sea levels plummeted, and vast coastal areas dried out. The oceans, once warm and fertile, became cold and barren. The marine food chain, the foundation of all life at the time, began to collapse. Species adapted to shallow waters simply lost their habitat. Thousands of organisms were trapped in frozen zones or stranded in retreating seas. What came next was the first global collapse of the biosphere. It is estimated that 85% of marine species disappeared. Corals fossilized into abandoned skeletons. Trilobites, once dominant, were reduced to a few resilient lineages. Marine life, until then the only existing form of complex life, faced its first great trial. Earth had become a blue-gray ball of ice, reflecting so much sunlight that the cold perpetuated itself in a cruel cycle. Ice stretched for thousands of kilometers, crushing continents, diverting winds, and imprisoning entire oceans beneath thick layers of silence. But, paradoxically, that same ice held the seed of salvation. As the glaciers advanced, they dragged along sediments rich in minerals, and when they finally began to melt, those nutrients returned to the seas. The thaw brought a flood of microscopic life, reactivating marine photosynthesis. The planet, in its own way of breathing, oscillated between collapse and recovery. This alternation between cold and warmth lasted for millions of years, and each cycle eliminated more species, but also opened space for new forms of existence. The survivors were few and resilient. Small organisms adapted to cold, capable of enduring low oxygen levels, thrived along the margins of the glaciers. Species that lived in deep waters, far from the frozen zones, managed to persist. It was in those dark refuges that life waited for the chance to begin again. When temperatures finally began to rise, the seas expanded once more. Meltwaters carried fertile sediments, and a new wave of diversification began. Earth, once again, rose from its own destruction. The evidence of this event remains etched in the rocks. Layers rich in oxygen isotopes record the advance and retreat of the glaciers. Fossils abruptly interrupted reveal the sudden extinction of entire lineages. The geological record clearly shows two phases of destruction, the first caused by extreme freezing, and the second, paradoxically, driven by the rapid thaw that followed. When the ice melted, enormous amounts of nutrients were dumped into the seas, triggering an uncontrolled proliferation of algae. Those blooms consumed the oxygen in the water, suffocating everything that remained alive. The planet had survived the ice, only to die by asphyxiation. Even so, This terrible episode was fundamental in shaping the Earth we know. It reorganized marine ecosystems and opened space for new species. Among the survivors emerged more adaptable organisms, with more efficient respiratory systems and more resilient bodies. This relentless selection forged the foundations of modern life. After the cold, the seas shone again. Corals reappeared, trilobites diversified once more, and new groups of fish began to arise. The Ordovician Silurian extinction had been devastating, but also liberating. The planet had learned a new lesson, that balance is fragile, and that every cycle of destruction renews diversity. From that point on, life began to occupy more varied niches, expanding into new depths and latitudes. The climate stabilized again, and a slow recovery stretched across tens of millions of years. It was as if Earth took a deep breath after a long nightmare. Today, looking back at this distant event, scientists see a pattern that would repeat many times. Every great extinction is preceded by climatic imbalance and accompanied by a total reorganization of the planet. Earth, in its geological wisdom, seems to use destruction as a tool for renewal. The Ordovician Silurian extinction was the first proof of this, a silent warning that life, however abundant it may seem, depends on a thin thread that the planet itself can snap at any moment. And even after this first great end, the world did not remain at peace for long. The newly achieved balance would once again bring excesses, transformations, and deaths, because on Earth, a new beginning never comes without a price. After millions of years of recovery, Earth bloomed once more. The ice had retreated, the seas had grown warm again, and life filled them anew. During the Devonian period, about 380 million years ago, the planet breathed a new balance. It was the age of fish, a time when the oceans teemed with creatures of shapes and sizes that would seem dreamlike to us today. Primitive sharks, armored fish with bony plates, and strange beings with powerful jaws ruled the waters. Corals built immense reefs, and plant life began to conquer dry land. It was a world in transition, and like every transition, it was about to be shaken. Plants had become a geological force. Deep roots penetrated the soil, releasing acids that wore away rock. This process freed minerals that, carried by rain, flowed into the seas. The photosynthesis of the forests increased the amount of oxygen in the atmosphere while reducing carbon dioxide. The climate began to cool, subtly, almost imperceptibly, yet steadily. This apparent triumph of plant life would also become the trigger for a new extinction. Once again, life itself would alter the planet enough to endanger its own existence. As forests spread across the continental margins, the soil began to accumulate organic matter that did not fully decompose. Carbon became trapped, and the greenhouse effect weakened even further. The oceans began to feel the consequences. The drop in temperature and the chemical imbalance caused a decline in dissolved oxygen levels. Entire regions of the sea turned into dead zones, unable to sustain life. Reefs that once shimmered with color began to fade. The blue of the oceans gave way to dark tones, and marine abundance collapsed. Volcanic eruptions made things worse. During the late Devonian, the planet experienced massive volcanic events that released toxic gases and ash into the atmosphere. The chemical balance of the oceans was destroyed. Acid rains fell upon the forests, and poisoned rivers carried heavy metals into the sea. The result was poisoning on a planetary scale. What the cold did not destroy, altered chemistry suffocated. The marine life cycle that had thrived for tens of millions of years dissolved in an instant on the geological timescale. The creatures that had ruled the seas, especially the large armored fish, nearly vanished. Trilobites, corals, and brachiopods suffered dramatic declines. The waters became murky and low in oxygen, and only the smallest and toughest species managed to survive. It is estimated that over 70% of marine species went extinct. Life on land, just beginning to take its first steps out of water, also felt the impact. Many of the first plants and primitive amphibians perished along with their habitats, unable to endure the extreme shifts in temperature and humidity. For a time, the planet fell into near silence. The atmosphere grew dense and cold, ocean currents stalled, and the rain carried the metallic taste of sulfur. The sun, filtered through layers of volcanic gas and dust, dimmed. It was a time of instability and darkness, an interval when Earth itself seemed to forget how to sustain life. Yet, as always, Chaos was preparing the ground for something new. Over millions of years, natural systems began to readjust. Volcanic ash, rich in minerals, fertilized the soils. Forests grew again, restoring cycles of moisture. The oceans slowly regained oxygen, and the dead zones began to shrink. Life returned, timidly, scattered, but persistent. Small bony fish, lighter and more adaptable, replaced the armored giants that had vanished. More resilient corals built new reefs, and along the swampy shores, a silent transformation began. Among the Devonian survivors were primitive amphibians, beings with sturdy fins that allowed them to support themselves on land for short periods. These organisms gave rise to the first terrestrial vertebrates. What began as a simple adaptation to oxygen scarcity in the water became the dawn of a new era. Animals were learning to breathe air, and Earth was witnessing for the first time the conquest of land. From ecological disaster was born the diversity that would dominate the ages to come. Geologists and paleontologists study the late Devonian as a turning point in the history of life. The rock layers from this time bear clear traces of catastrophe, dark deposits of accumulated organic matter, evidence of oceanic anoxia, and fossil records abruptly cut short. It is the portrait of a world that nearly collapsed under the weight of its own transformations, but also proof that destruction paves the way for biological innovation. The planet did not merely recover what it had lost, it reinvented itself. After the Devonian, life would never be the same. The planet had learned to survive across multiple environments. Forests expanded into the continents, and the first complex ecosystems appeared on land. The extinction of the great fish opened ecological space for new lineages of vertebrates and invertebrates. Even the atmosphere changed. The balance between oxygen and carbon dioxide became more dynamic, regulated by the interaction between plants, soil, and oceans. What had begun as a crisis ended as a metamorphosis. The planet's second great collapse proved that life does not merely resist, it transforms. Extinctions are not endings, but pauses between acts of the same geological play. Each event reshapes the stage and redefines the characters. In the Devonian, the planet nearly succumbed to its own fertility, but from the ashes emerged the first signs of terrestrial life. It was the prelude to a new era, one in which Earth would die and be reborn on even grander scales. The world had survived once again, but the balance was an illusion. Beneath the surface, colossal pressures were building, and the winds of destruction were already stirring. The next act in Earth's history would be the darkest of all. The true apocalypse was yet to come. The planet had learned to survive, but not to rest. After the Devonian, life flourished with astonishing vigor. Forests covered entire continents, the seas were vast and filled with bizarre creatures, and the first reptiles began to spread across dry regions. The world was full of possibilities, and every species seemed to occupy its place within the natural balance. But beneath the surface, something terrible was brewing. Earth was preparing for the greatest destructive event in its entire history, a collapse so profound it would erase almost everything that had evolved until then. This event would become known as the Permian extinction, the moment when Earth almost completely died. The setting was a planet very different from the one we know today. All continents were united into a single colossal landmass, Pangaea, an immense supercontinent surrounded by a global ocean called Panthalassa. This extreme configuration created equally extreme climates. The inner regions of Pangaea were arid, hot, and inhospitable, while the coastal zones were temperate and fertile. The absence of inland seas prevented thermal balance, and the planet swung between scorching droughts and devastating storms. Even so, life thrived. Reptiles diversified, insects grew to colossal sizes, and forests of conifers and giant ferns dominated the landscape. It was a vibrant world, and it was about to fall apart. Everything began with fire. Around 252 million years ago, a sequence of monumental volcanic eruptions began to devastate what is now Siberia. These eruptions lasted not for days or centuries, but for more than 1 million years. Millions of cubic kilometers of lava were released, covering vast territories and spewing colossal amounts of gases into the atmosphere. Carbon dioxide, methane, sulfur, and other toxic compounds poisoned the air. Earth's climate collapsed. Average temperatures rose rapidly, The greenhouse effect, intensified by the staggering accumulation of gases, turned the planet into a suffocating furnace. The oceans began to absorb the excess carbon dioxide, becoming increasingly acidic. Warm water lost its ability to hold oxygen, and vast marine regions turned anoxic, zones devoid of any life. Everything that depended on oxygen began to die slowly. Marine creatures, which had dominated the planet for hundreds of millions of years, were the first to perish. Corals vanished, trilobites were finally wiped out, and almost every shelled or skeletal organism dissolved in the acidic seas. Meanwhile, on land, the air became toxic. Acid rains burned entire forests. The soil lost its nutrients and plants could no longer regenerate. With vegetation gone, terrestrial food chains collapsed. Giant insects, which had thrived for millions of years, disappeared completely. Reptiles and amphibians died en masse, unable to find shelter or food. The planet entered a state of near-total desolation. It is estimated that 95% of all species were exterminated. It was the lowest point in the history of life on Earth. The late Permian landscape was hellish. The ground was cracked and covered in ash, the air thick and unbreathable, the sky filled with soot and red lightning. The sun, dimmed by sulfur particles, shone like a distant lamp behind a veil of smoke. Electric storms crossed the scorched continents, and the oceans, saturated with gas, released methane bubbles that ignited the surface in blue flames. For millennia, the planet burned. The balance that had sustained the biosphere was irreversibly broken. Earth had become a burning, silent wasteland. Yet even in this total ruin, life refused to vanish. In the oceanic depths, microorganisms adapted to oxygen-deprived environments continued to thrive. Methanogenic bacteria, capable of surviving in toxic conditions, formed colonies in hydrothermal vents. Small reptiles and insects, sheltered in underground refuges, endured the waves of heat and darkness. They were few, but enough to preserve the fragile continuity of life. In its agony, the planet kept a spark of survival hidden in the shadows. After millions of years of devastation, volcanism began to subside. Rains gradually cleansed part of the atmosphere, and the climate slowly began to stabilize. Temperatures fell and new forests started to grow in the wetter regions. The soil regained part of its nutrients, and the cycle of life reorganized itself. However, the Earth that emerged from the Permian was unrecognizable. The dominant species were gone. The ecosystems had been reconfigured. It was as if the planet had been reset, a blank page in the book of evolution. Scientists call the Permian event the Great Dying, and rightly so. No other moment in geological history was so catastrophic. The planet nearly lost its ability to sustain complex life. Yet it was precisely this annihilation that cleared the way for something new. The few survivors, small reptiles, heat-resistant plants, and microorganisms, became the ancestors of the lineages that would dominate Earth's next chapter. The world had burned to its limit, and from the ashes, a new cycle was about to begin. The Permian apocalypse was not only the greatest biological disaster ever recorded, it was also the turning point that prepared the planet for the rise of dinosaurs, mammals, and, much later, ourselves. Fire, death, and silence gave way to rebirth. Once again, Earth proved that even in the face of absolute extinction, life always finds a way to persist. The planet exhaled after the destruction, a hot, weary breath, yet full of promise, because in its cyclical nature, Earth does not know the concept of an end, only that of a beginning. Earth had passed through hell. After the great dying of the Permian, the planet was unrecognizable. Continents charred, oceans poisoned, air thick with ash. Life, reduced to a handful of scattered survivors, stood on the brink of complete extinction. But the story of Earth never ends in silence. Slowly, after millions of years of devastation, the world began to breathe again. It was the dawn of a new era, the Triassic, a time of reconstruction when the wounded planet learned to rise from its own ashes. The first millions of years after the Permian were unstable. The climate still fluctuated between extreme heat and cooling periods. Volcanoes continued to release gases, and the atmosphere struggled to regain its lost chemical balance. The seas, saturated with carbon dioxide, remained acidic and murky, yet gradually new food chains began to form. Bacteria and microscopic algae reappeared, followed by small crustaceans and mollusks. Life once again began from the bottom, rebuilding what had been erased. On land, the scenery was desolate. The forests were gone, replaced by red deserts and immense dunes. Acid rain still fell in some regions, corroding rock and depositing minerals into rivers. Even so, small pioneering plants began to emerge, mosses, lichens and ferns that grew on newly formed soils. They prepared the ground for the return of larger vegetation. This vegetal rebirth was vital. It restored oxygen to the atmosphere and helped stabilize the climate. The planet was, little by little, rebuilding its own respiration. Animals also began to diversify. Small reptiles, descendants of the few that had survived the Permian, started exploring new environments. Some adapted to riverbanks, others to arid lands. These creatures would become the ancestors of groups that would dominate Earth for millions of years. Among them were the first archosaurs, a group of reptiles that would give rise to both dinosaurs and crocodiles. Small, fast, and heat-resistant, they thrived where other forms of life could not survive. As animals reclaimed the land, the planet underwent profound geological changes. Earth's internal forces began slowly fracturing Pangaea. Fissures opened, oceans began to form, and the map of the world was once again being redrawn. This fragmentation released energy and gases that helped stabilize global temperatures. Thermal balance returned, and with it, life's diversity accelerated. The oceans, now less acidic, became fertile once again. Corals began to grow, and new species of fish appeared. Small amphibians that had survived the Permian shared the seas with newly evolved marine reptiles such as ichthyosaurs, streamlined creatures that resembled primitive dolphins. They represented one of life's first attempts to reclaim the open ocean after total destruction. Biological diversity expanded in all directions, and the planet began to regain its lost brilliance. In the Triassic world, extremes ruled. Seasons were unpredictable, arid climates prevailed in many regions, and lightning storms were frequent. The lack of dense vegetation made the heat reflect intensely off the ground, creating vast desert zones. Yet life persisted. Seed-bearing plants, such as conifers, began to dominate the landscape. They no longer depended on water to reproduce, giving them an immense advantage in a dry world. With the return of forests came insects, small vertebrates, and gradually, predators. It was in this adaptive environment that the first dinosaurs appeared. They were not yet giants, small, light, and swift. Their body structure allowed them to endure heat and travel great distances in search of food. Meanwhile, other reptiles developed membranous wings and learned to glide among the trees. These were the first pterosaurs, pioneers of the skies. The Earth, once a stage of ash and silence, now echoed once again with the sound of life in motion. But reconstruction was not linear. Several waves of smaller extinctions occurred during the Triassic. Volcanoes remained active, releasing toxic gases that sometimes darkened the skies for decades. The planet, still unstable, seemed to be testing its own endurance. Yet every crisis was followed by a new burst of evolution. Diversity grew with every challenge. The young ecosystems were learning to balance energy, climate, and organic matter. Life was stronger, more adaptable, more inventive. In the depths of the oceans, organisms began developing new survival strategies. Mollusks and ammonites built shells more resistant to acidity. Fish diversified in size and shape. Corals evolved into compact colonies capable of enduring extreme temperature fluctuations. On land, the first primitive mammals, descendants of synapsids, began to appear. They were small, nocturnal, and covered in fine hair. This new trait, the regulation of body temperature, would become one of evolution's great keys to future success. The Triassic reconstruction was an age of experimentation. The entire planet seemed to be testing new forms of biological organization, as if seeking harmony after chaos. Life, now marked by the memory of destruction, had become more creative and resilient. Everything that had survived the Permian possessed an almost supernatural endurance, an adaptability that would shape the next 200 million years of Earth's history. When Pangaea began breaking apart more intensely, the climate changed again. The continental edges grew fertile, and vast lakes and rivers appeared, giving rise to new ecosystems. The first dinosaurs began to diversify. Some became sturdy herbivores, others swift and lethal predators. In just a few million years, they would occupy nearly every habitat on the planet, but a shadow still loomed ahead. The Triassic, though an age of rebirth, would end abruptly with a new extinction that would pave the way for the final dominance of the dinosaurs. The cycle of destruction and renewal was far from over. Earth, true to its pattern, was already preparing its next chapter. The planet had survived fire, suffocation, and solitude. Now it was rebuilding, learning to live again. But as with every story on this world, balance would only be temporary. Life did not yet know it, but another collapse was coming, and with it, the birth of an age of giants. The Triassic had been the stage of reconstruction, the slow return of life after the greatest catastrophe in Earth's history. But as always, the balance that nature achieves is only a pause between two extremes. After millions of years of recovery, the planet began to change once more. What had started as a rebirth would culminate in yet another global extinction. The Triassic-Jurassic extinction would become the fourth great collapse of the biosphere, a violent transition that opened the path for the dominance of the dinosaurs and a new configuration of terrestrial life. Earth was no longer the same world it had been during the Permian. The continents, still joined in the vast Pangaea, had begun to fragment. Deep fissures cut across the supercontinent, and magma rising through these cracks formed immense basalt plains. It was the beginning of the separation that would later shape the continents we know today. This geological rupture released colossal amounts of carbon dioxide and methane, gases that quickly transformed the climate. The planet, once dry and irregular, entered a new cycle of warming. Global temperatures rose abruptly. Regions that had been temperate became desert-like. The polar caps disappeared. The seas evaporated faster, and the resulting moisture fueled violent storms that swept the continental margins. The chemistry of the oceans began to shift. Acidity increased, and vast areas became anoxic. Marine creatures, especially corals and mollusks, suffered a dramatic collapse. In just a few 100,000 years, entire food chains disintegrated. The sea, the cradle of life since its origin, once again became a hostile place. Meanwhile, volcanic eruptions continued without rest. The planet seemed to pulse with fire from within. Scientists call this sequence of events the Central Atlantic Magmatic Province, one of the largest volcanic episodes ever recorded. The carbon dioxide expelled from these eruptions drastically altered the atmospheric balance, creating a runaway greenhouse effect. Forests began to dry, soils cracked, and species adapted to the stable Triassic climate could not react in time. The air grew hot, heavy, and filled with dust. Acid rains fell once again, destroying vegetation and altering the chemistry of rivers and lakes. The consequences were devastating. It is estimated that around 80% of all species from the Triassic period disappeared. In the seas, ammonites and primitive fish were wiped out. On land, many reptiles and amphibians, including large apex predators, were completely extinguished. Landscapes once teeming with diversity became empty and silent. Forests turned into scorched plains, and the planet once again fell into prolonged collapse. It was as if Earth, still weary from the Permian, had been forced to die once more. But as always, destruction created space for new beginnings. In the intervals between eruptions, the excess carbon dioxide boosted photosynthesis in surviving plants. Species resistant to heat and drought spread quickly. Small, lightweight, and agile reptiles, among them the early dinosaurs, began to thrive. Unlike their predecessors, they were better at regulating body temperature, had upright postures, and possessed hollow bones that allowed for greater mobility. In a world of extremes, lightness became an evolutionary advantage. As ecosystems rebuilt themselves, these dinosaurs multiplied and diversified. With the extinction of the large Triassic predators, the way was clear for them to become the new rulers of Earth. Massive herbivores began to roam through the regenerating forests, while carnivores developed sharp teeth and bodies adapted for hunting. It was the beginning of an absolute dominance that would last for the next 150 million years. After yet another cataclysm, the planet found a new balance in the shadow of giants. The oceans too found new masters. Bony fish diversified, and marine reptiles such as ichthyosaurs and plesiosaurs became the dominant predators. The cycle of life restarted in all directions, carrying with it the scars of what had been lost. The species of the Jurassic were born from a transformed world, where every organism was a direct product of the selective pressures imposed by the previous catastrophe. Earth had undergone another natural filtering, a brutal selection that erased what could not adapt and rewarded what could. Scientists study the Triassic-Jurassic extinction as a boundary between eras. The evidence preserved in rock layers reveals an abrupt transition marked by alternating strata of basalt and volcanic ash mixed with fossil remains. Carbon isotopes record violent oscillations in atmospheric composition. It is a clear portrait of how the planet reacts unpredictably to internal disturbances. Even the best adapted species can vanish when Earth decides to rewrite its own rules. This event was less explosive than the Permian extinction, yet equally decisive. It erased the old world and opened the stage for the most famous chapter in natural history, the age of the dinosaurs. The creatures that survived emerged into a renewed planet where heat, humidity, and vegetation abundance created ideal conditions for the rise of the largest animals ever to walk the Earth. It was the dawn of the Jurassic, a time when life would reach a new height of diversity and splendor. The Triassic-Jurassic extinction was both an end and a beginning, a collapse that destroyed one world and prepared the ground for another. And once again, Earth proved that every death is only the interval before a new form of life emerges. After millions of years of chaos and fire, the planet began to breathe again. The Triassic had ended in flames, but from the ashes arose a new world, greener, wetter, and more fertile. It was the dawn of the Jurassicus, a period when Earth was reborn on a grand scale. Forests expanded, the seas grew warm and filled with life, and the skies began to swarm with creatures that challenged the very limits of the air. The planet had rebuilt itself, and now it belonged to the dinosaurs. The Jurassic world was a tropical paradise. The fragmentation of Pangaea had created inland seas and continents surrounded by lakes and humid plains. Moisture fed constant rains, and the steady heat made forests lush and dense. Giant ferns, cycads, and conifers dominated the landscape, forming ideal environments for the rise of creatures of colossal proportions. It was in this setting that dinosaurs ceased to be small survivors and became the largest land animals of all time. The diversity that emerged was extraordinary. Gigantic herbivores such as the sauropods grew to lengths of dozens of meters. Their long necks allowed them to reach the highest tree canopies, while their heavy, flexible tails served as weapons against predators. Each step of these animals made the ground tremble, and the rhythm of their movement echoed across the plains like the living heartbeat of the planet. In contrast, predators such as the allosaurs became agile and intelligent, hunting in groups and adapting to ever larger prey. Earth had become a theater of giants. The oceans, too, pulsed with renewed life. Modern corals rebuilt colorful reefs, and mollusks such as ammonites filled the seas in vast numbers. Marine reptiles dominated the open waters. Ichthyosaurs, resembling dolphins, sliced through the sea with incredible speed, while plesiosaurs, with long necks and powerful flippers, ruled the depths. Marine life flourished as never before, and the planet's ecological webs grew more intricate and interconnected. It was a world that seemed to have finally found harmony. In the skies, new forms of life emerged. The pterosaurs, descendants of Triassic reptiles, became the masters of the air. Their membranous wings reached enormous spans, and many displayed vivid crests and complex social behavior. They were the first vertebrates to achieve true powered flight, inaugurating a new domain of life, the aerial realm. The sky, once silent, now came alive with gliders and winged hunters soaring above forests and coasts. It was a three-dimensional biological spectacle. Meanwhile, small primitive mammals hid in the shadows. Descended from synapsids, they were discreet, nocturnal, and lived under the absolute dominance of the giant reptiles. They fed on insects, flowers, and small fruits. Their apparent insignificance concealed a profound importance. These tiny survivors represented the continuation of a lineage that would one day inherit the planet. But for now, they were only silent witnesses to the age of giants. The Jurassic was a time of abundance, but also of fragile balance. Life had become exuberant, yet it depended on stable climate patterns and intricate ecosystems. Minor changes in oceanic currents or volcanic activity could cause local disturbances, but Earth remained fertile and alive. Still, that balance carried the same destiny as all before it. It was temporary. No biological empire lasts forever. Scientists believe the dinosaurs' success resulted from a combination of geological and biological factors. The fragmentation of Pangaea created many isolated environments, and isolation fostered diversity. Species evolved apart from one another, adapting to different climates, plants, and predators. Earth became a vast evolutionary laboratory, where experimentation never ceased. This multiplication of forms and survival strategies made dinosaurs the most successful group ever to exist. But their success was not merely physical. Many developed complex social behaviors, migrated in groups, and protected their offspring. Fossils found with preserved nests and eggs reveal that several species cared for their young, a behavior that challenged the notion of cold, instinct-driven reptiles. This new biology, founded on cooperation, adaptation, and care, was what allowed them to rule the planet for more than 150 million years. The Jurassic also witnessed a silent transformation in the air and among the plants. The first flowers had not yet appeared, but the conifer and fern forests created rich and diverse ecosystems. The carbon cycle had stabilized, and the planet became a self-regulating system. It was as if Earth, after so many collapses, had finally learned to sustain life in balance. For a while, the planet seemed truly at peace, but balance always demands a price. Volcanic activity still persisted, and ocean currents were slowly changing. The climate began to cool in some regions and grow wetter in others. These subtle shifts triggered mass migrations and species replacements. Yet the dinosaurs continued to thrive. For every group that vanished, another arose. The planet seemed to live by the cyclical rhythm of natural renewal. The age of giants was more than the reign of the dinosaurs. It was the peak of complex life on the planet. The biosphere was at its highest level of productivity. Every continent, every ocean, pulsed with abundance and variety. The planet had ceased to be a victim of catastrophe and had become a machine for generating life. The silence of the post-Permian world had transformed into a chorus of voices, roars, and the beating of wings. For the first time, Earth seemed to have conquered death itself. However, the cycle of destruction never sleeps for long. What is born from catastrophe carries within it the seed of the next collapse. The continents continued to drift apart, and beneath the shifting tectonic plates, ancient pressures began to build once more. The planet was again in motion, and the balance of the Jurassic would soon be tested. The giants ruled, but above them, among the stars, another destiny was already unfolding. A distant visitor, a wandering rock traveling through the void, was slowly approaching Earth. The future of the world was being prepared, and when that rock finally struck the planet, nothing would ever be the same again. For now, however, the planet lived at its zenith. Life had reached the highest point in its history, and the roar of the dinosaurs echoed like the beating heart of the Earth itself. The planet was more alive than ever. Dinosaurs ruled the land, the seas, and the air. Forests grew dense and lush, and the climate was warm, stable, and fertile. Earth during the Cretaceous, around 140 million years ago, was a biological paradise, an era of expansion and abundance. The fragmentation of the continents had accelerated diversity, creating new environments and new forms of life. It was the peak of the age of giants, but also the beginning of a silent transformation that would change the planet forever. The continents were now farther apart than in the Jurassic. The supercontinent Pangaea had split into smaller landmasses, forming inland seas and long mountain ranges. Ocean currents became more complex, regulating temperature and carrying moisture to regions that had once been dry. Forests covered vast plains, and the oceans teemed with fish, mollusks, and colossal marine reptiles. The planet seemed to have reached the perfect balance between warmth and life. But what nature calls balance is, in truth, only the brief pause before change. It was during the Cretaceous that one of the most important events in biological history occurred, the emergence of flowering plants. Until then, Earth had been dominated by conifers, ferns, and cycads. But now, a new type of plant, the angiosperms, began to spread. They bore flowers, fruits, and protected seeds, giving them an enormous evolutionary advantage. The flowers attracted insects, and the insects, feeding on nectar, carried pollen from plant to plant. It was the beginning of an evolutionary partnership that would shape Earth's future. The symbiosis between plants and pollinators the planet filled with color, scent, and new flavors, and the foundation of the food chain began to change. With the flowers came the modern insects: bees, butterflies, beetles, and wasps. This explosion of diversity fueled a new generation of herbivores and predators. Dinosaurs adapted their diets and behaviors. Herbivorous species developed stronger jaws and complex teeth capable of grinding tough leaves. Carnivores, in turn, became faster and more strategic. The ecosystems of the Cretaceous were dynamic and interconnected, sustained by a constant flow of energy between plants, insects, and reptiles. The planet had become a living organism, pulsing in perfect rhythm. In the oceans, life also flourished. New species of marine reptiles appeared, such as the mosasaurs, colossal predators up to 15 meters long that hunted fish, turtles, and even other reptiles. Ammonites with their spiral shells dominated the seas, while schools of bony fish formed true storms of glittering scales. The ocean floor was its own universe, full of corals, crustaceans, and mollusks, all part of the endless cycle of life and death that kept the biosphere active. The warm, stable climate allowed vast tropical forests and enormous swamps to form. Regions that are now deserts were then covered by dense vegetation and wide rivers. The air contained higher levels of oxygen than today, and every breath fed organisms abundantly. This atmospheric richness was one of the reasons dinosaurs could reach such immense sizes. The entire world was a system of expanding energy. Earth seemed invincible, and life eternal. But beneath this splendor, something was beginning to change. Geological forces were still in motion, and with them the planet's delicate balance. Volcanic activity was slowly increasing, releasing gases and particles into the atmosphere. Ocean currents began to shift, and carbon dioxide levels fluctuated irregularly. Subtle climate variations caused droughts in some regions and floods in others. Species accustomed to stability began to vanish in silence, replaced by others more resilient. It was as if the planet itself were preparing for something. Even so, life went on. New species emerged with every passing million years. The Cretaceous was also the era of the rise of primitive birds, direct descendants of theropod dinosaurs. Flight, once belonging solely to the pterosaurs, had now become an even more refined biological tool. Feathers, which originally served for thermal insulation, had evolved into instruments of aerodynamics and beauty. The sky, once ruled by gliding reptiles, was now crossed by agile and graceful birds. Life had learned to conquer every element, land, sea, and air. But while the dinosaurs reigned over the surface, small mammals continued to live discreetly in the shadows. They were tiny, nocturnal, and nimble, with sharp senses and expanding brains. They fed on insects and fruit, evading larger predators. Though they seemed insignificant, they were the seed of a distant future. Nature had hidden within them a new form of intelligence and adaptability that would one day redefine the planet's destiny. The end of the Cretaceous was drawing near, and with it, a sequence of catastrophic events began to align. Volcanism in the region that now corresponds to India intensified, forming the Deccan Traps, immense eruptions that lasted hundreds of thousands of years. Millions of cubic kilometers of lava were expelled, releasing gases that altered the composition of the atmosphere and oxygen levels. The climate became unpredictable, the seas began to acidify, and the ecological balance was shaken. As the planet struggled to adjust, a distant visitor approached in silence, a gigantic asteroid wandering through the void for millions of years, drawn by Earth's gravity. Its fate was already sealed, and its collision would mark the end of an era. Yet no one could have foreseen the magnitude of the transformation that was about to unfold. The planet that had been reborn so many times was about to face the swiftest and most destructive blow in its entire history. The Cretaceous was the peak of life, and the prelude to death, a magnificent world standing on the brink of an eternal night. And the impact that approached would not only end the reign of giants, but also open the path for the rise of a new kind of life, fragile, small, and conscious. The planet was living the height of life. Dense forests covered the continents, warm seas sheltered endless schools of fish, and colossal creatures roamed the earth with majesty. It was the end of the Cretaceous, and the world seemed stable, fertile, and indestructible. But hundreds of millions of kilometers away, a wandering visitor drifted through the emptiness of space. It was an ancient rock, a relic from the formation of the solar system, traveling for eons without purpose. Its name would be known long after, Ancient Chicxulub, and the day of its arrival would mark the end of an era, the day the entire planet would plunge into darkness. The asteroid was about 10 kilometers in diameter, composed of metal, stone, and ice, a colossal mass moving at more than 20 kilometers per second. When it entered Earth's atmosphere, it shone brighter than 1,000 suns. The friction with the air wrapped it in a halo of fire, and for a few brief moments, the sky of the entire planet was illuminated by a flash no living creature could comprehend. The impact occurred where the Yucatan Peninsula lies today, in the region now known as Mexico. In less than a second, the energy released equaled billions of atomic bombs. The shockwave was instantaneous. Rocks melted, the ground fused, and a crater nearly 200 kilometers wide opened in Earth's crust. The ocean was thrown upward in columns of vapor and molten magma. Everything within hundreds of kilometers was vaporized. Forests, rivers, mountains, all turned to dust and fire. The planet screamed, and life, unable to understand, fell silent. The impact did not destroy only one region, it changed the entire planet. Seismic waves rippled across the globe, triggering earthquakes that made the continents shudder. Dormant volcanoes awakened in successive eruptions, releasing toxic gases and ash. The atmosphere was filled with fragments of rock and sulfur, hurled tens of kilometers high. The sky darkened within hours. A permanent twilight consumed the earth. The sun vanished for months, perhaps for years. It was the beginning of what scientists call the impact winter, an age of extreme cold, darkness, and death. On the first day, the heat of the impact incinerated everything exposed. Entire forests were reduced to charcoal. Animals burned alive, and the seas boiled with steam. On the second day, the heat gave way to night. The particles suspended in the stratosphere blocked the sunlight. Global temperatures plummeted, and the planet sank into a long age of darkness. The cycle of photosynthesis came to a halt. Plants died, herbivores succumbed to hunger, and carnivores soon followed. The web of life, woven over millions of years, unraveled in a matter of weeks. The acid rains began to fall soon after. Sulfurous particles mixed with water to form corrosive storms that devastated ecosystems. Lakes and rivers turned toxic. The soil, drenched in acid, lost its fertility. Even in the deep oceans, life was shaken. The excess of debris blocked out light, and the temperature of the waters plummeted. Phytoplankton, the foundation of the entire oceanic food chain, died in massive numbers. The seas became cold, dark deserts. With each passing day, fewer beings remained alive. The planet seemed to return to the lifeless state it had known during the Permian. The dinosaurs, undisputed rulers of Earth for more than 150 million years, were the most emblematic victims. The giant herbivores starved and froze. The predators, deprived of prey, soon followed. Nests carefully built were buried under ash. The roar of the titans fell silent. In just a few thousand years, a geological instant, the age of giants came to an end. Only small lineages survived: primitive birds, crocodiles, and a few resilient mammal species. The dominion of the dinosaurs ended in silence, and once again, the planet had to begin anew. The crater left by the Chicxulub impact became a deep scar, a geological reminder of the fragility of life. For a long time, scientists debated whether this event alone caused the extinction or if it coincided with the volcanism of the Deccan Traps. Today, the evidence is clear. Both occurred almost simultaneously, creating a perfect storm. The impact threw up enough dust to block the sun, while volcanism continued releasing carbon dioxide into the atmosphere for hundreds of thousands of years. The planet was trapped between cold and heat, unable to stabilize. It was the complete collapse of global climate. But as with every end, there was the seed of a new beginning. Amid the ruins and ashes, small mammals emerged. They had survived hidden in burrows, feeding on seeds, roots, and insects. When the world brightened once more, they were the ones left to rebuild life. Forests began to grow again. The climate softened, and the oceans regained their blue. In a few million years, new species filled the void left by the giants. The planet had changed its guardians. The Chicxulub impact was the fastest and most devastating event in the planet's history, but also the most decisive. It not only ended the reign of the dinosaurs, but opened the path for the rise of mammals, and eventually humanity. Chaos and destruction gave birth to intelligence and consciousness. The end of the giants was the dawn of a new age of perception. The moon, a silent witness to the collision, reflected for nights the reddish glow of Earth's ashes. It seemed to weep, veiled in the reflection of a mourning world. It was as if the cosmos itself lamented the loss of a planet once full of life. Yet life, resilient as ever, was already preparing its return. Even amid the cold and darkness, the planet never stopped trying to live. And once again, Earth rose from the abyss. The Chicxulub impact was the final blow of an era, but also the omen of our own existence. Life had died only to one day learn to think about death. When silence took over the Earth after the impact, it seemed that everything had ended. The sky remained covered, the oceans were cold, and the forests had been reduced to ashes. For a while, the planet seemed to have forgotten life itself. But beneath the dark soil, in the cracks of rocks and the depths of caves, small survivors waited. They were not as imposing as the dinosaurs, nor as dominant as the reptiles of the past. They were fragile creatures, the size of mice, covered in fine fur and endowed with an instinctive intelligence that had kept them alive when the world fell apart. These small beings would become the new heirs of the Earth, the mammals. In the first thousands of years after the impact, the planet was still hostile. Temperatures remained low, vegetation was scarce, and acid rains continued to fall at unpredictable intervals. But little by little, the atmosphere began to clear. The cosmic dust dissipated, and sunlight once again broke through the clouds. Warmth returned, and with it, photosynthesis. Plants were the first to be reborn, mosses, ferns, and small herbs. Then came the forests. Oxygen increased, and the planet began to breathe again. And when Earth breathes, life always answers. The mammals, until then discrete inhabitants of the shadows, began to expand. Their ability to regulate body temperature gave them a great advantage in an unstable world. While reptiles still depended on external heat, mammals could keep themselves warm even in the cold. Moreover, their internal gestation protected their offspring from harsh conditions, and their parental care improved survival chances. They were few, but they were persistent, and that persistence would change everything. As forests began to cover the continents once more, mammals diversified. Some adapted to life in the trees, others became swift runners on open plains, and some returned to the sea. The planet, now free from the giants, became an open field for biological experimentation. Ecosystems reorganized, and every empty niche became an opportunity. In just a few tens of millions of years, mammalian diversity exploded. The first ungulates appeared, ancestors of horses and deer. The cetaceans, which returned to the ocean and gave rise to dolphins and whales. And the primates, curious creatures that would learn to observe and manipulate the world around them. The oceans also transformed. Without the marine reptiles of the Cretaceous, new species of fish and aquatic mammals took control of the seas. The ammonites disappeared, but corals rebuilt vibrant reefs. Marine food chains regained balance, and phytoplankton photosynthesis returned the blue to the waters. The planet began to pulse again, more delicate, but more stable. Life found its way, as it always had, even after the apocalypse. The climate of the following period, the Paleocene, was marked by a slow warming. Earth was recovering the energy it had lost during the impact winter. Tropical forests spread again, covering entire continents. The atmosphere filled with vapor and oxygen, and the cycle of rains became regular. Ecosystems flourished, and with them, mammals grew in both number and size. The descendants of the small creatures that had survived in burrows began to occupy the place once held by dinosaurs. It was a new kind of dominion, unlike any before, a dominion of intelligence, flexibility, and warmth. But post-impact life was not just reconstruction, it was reinvention. Mammals developed sharpened senses and larger brains. Night vision, keen smell, and refined hearing became essential tools for survival. They adapted to their environment not through strength, but through perception. This behavioral shift was the seed of something unprecedented, the ability to learn. The evolution of intelligence was no accident, but a response to the planet's instability. Each challenge demanded memory, strategy, and adaptation, traits that would shape the future of life on Earth. Meanwhile, the planet continued to transform. The fragmentation of the continents advanced, and ocean currents redefined the climate. The rise of carbon dioxide brought intense heat waves, followed by sudden cooling periods. Life, once again, danced between extremes. But now there was a difference. Mammals could migrate, seek shelter, and modify behavior in response to change. They did not merely survive. They learned how to survive. And that made all the difference. Fossil records from this era reveal an Earth in full renewal. In just a few million years, mammals had conquered every environment. Small rodents and carnivores roamed the Paleocene forests. Large herbivores spread across the plains of the Eocene. And in the skies, birds of prey reclaimed the role of the extinct pterosaurs. Nature had reinvented balance. No single form of life ruled completely, and diversity became the foundation of stability. The planet seemed to have learned from its own catastrophes. Over time, primates began to stand out. With binocular vision and grasping hands, they developed coordination and curiosity. Living among the treetops, they observed, experimented, and remembered. Every leap from branch to branch was also an evolutionary leap toward consciousness. From these ancestors would later emerge a lineage that would one day look to the stars and wonder where it came from. But at that distant moment, they were only small creatures, surviving in the shadows of a new world. The planet had changed. The seas were clearer, the air purer, and the climate milder. The great reptiles belonged to the past, and life moved to a new rhythm. For the first time since the dawn of existence, Earth seemed to belong to beings who did not need brute force to dominate. What sustained the future now was the ability to think, to feel, and to care. The fire of destruction had become the light of consciousness. The age of mammals had begun, and in the silence after the catastrophe, the planet once again was beginning its own story anew. The history of Earth was never linear. Between the great cataclysms that nearly erased life, there were others, smaller in scale but equally significant in consequence. These were events that, although they did not destroy most species, redefined ecological balance, opened space for new forms of life, and ended biological empires that once seemed eternal. These cycles of destruction and silent renewal are known to scientists as minor extinctions, episodes of evolutionary cleansing in which the planet reorganizes its own complexity. The first of these extinctions after the rise of mammals occurred during the Eocene around 50 million years ago. Earth's climate, which had been warming since the end of the Chicxulub impact, reached a boiling point. Average global temperatures were extremely high, and the poles were nearly free of ice. Tropical forests extended into regions that are now cold, and the oceans teemed with life. But the excess carbon dioxide, accumulated through intense volcanism and organic decomposition, created a dangerous imbalance. Small increases in temperature triggered the Paleocene-Eocene thermal maximum, one of the fastest and most intense global warming events in Earth's recent history. During this episode, the polar ice caps melted almost completely, releasing methane trapped in permafrost and deep ocean sediments. This gas, far more potent than carbon dioxide, accelerated the warming, creating a runaway cycle. The oceans became acidic, oceanic circulation changed, and many marine species vanished. Yet terrestrial life flourished in unexpected ways. New plants and mammals adapted to the heat, expanding toward the poles. It was a moment of ecological reorganization, a redistribution of life that prepared the planet for its next chapter. When the heat finally subsided, the planet experienced a brief equilibrium, but soon the pendulum swung again, this time toward the cold. During the Oligocene, about 34 million years ago, ice returned. Sea levels fell, and vast coastal areas turned into arid plains. Species adapted to tropical warmth were pushed toward equatorial regions, while new forms of life emerged in colder zones. Mammals began to grow larger, developing dense fur and fat reserves. Life was learning once again to respond to extreme changes. These fluctuations in temperature and atmospheric chemistry acted as evolutionary filters. With each new cycle, some species disappeared, and others, more adaptable, took their place. Nature seemed to test its own limits, erasing what no longer worked and experimenting with new genetic combinations. Throughout the Miocene and Pliocene, between 25 and 3 million years ago, Earth experienced countless such adjustments. Periods of intense volcanism, tectonic shifts and variations in the planet's rotational axis created micro-ecological catastrophes that lasted thousands of years. These so-called minor extinctions reshaped the planet's ecosystems with the same creative force as the great cataclysms. During the Miocene, for instance, the collision of the Indian subcontinent with Asia gave birth to the Himalayas, profoundly altering the global climate. Monsoons emerged, winds reorganized, and new biomes were born. Dense forests turned into savannas, and animals that once lived among trees had to learn to run, hunt, and see from a distance. It was in this environment that the ancestors of felines, equids, and primates developed their modern traits. Every geological change generated an immediate biological response. The oceans also underwent dramatic transformations. The gradual closing of the connection between the Atlantic and the Pacific, with the formation of the Isthmus of Panama, changed ocean currents and intensified the transport of heat between hemispheres. This triggered a redistribution of species and at the same time a new wave of extinctions. Marine organisms that depended on warm waters saw their habitats vanish, while others migrated and evolved. Marine biology became a dynamic mosaic driven by each tectonic and climatic shift. The fossil record shows that these minor extinctions acted as mechanisms of natural regulation. They prevented the planet from entering prolonged states of imbalance and stimulated biological innovation. Without these cycles of cleansing, many lineages would have become overly dominant, stagnating evolution. The very diversity that exists today is the result of these small losses and recoveries. In geological terms, Earth does not destroy out of malice, it reorganizes. However, each of these transformations left deep traces. Layers of volcanic ash, marine sediments, and fragmented fossils tell stories of abrupt changes and forced adaptations. Each period bears a unique signature, variations in carbon ratios, oxygen records, and traces of heavy metals. These are the chemical scars of a planet in constant reconstruction. Within them, we can read the history of the lives that came and went, silently, between one great catastrophe and another. When the planet entered the Pleistocene just over 2 million years ago, a new sequence of changes began. Colder, more rhythmic, and in a way, more predictable. Glaciations became part of Earth's cycle, covering entire continents with ice and then retreating. These ages of cold were the last great trials before the arrival of humankind. Species of mammoths, saber-toothed tigers, and woolly rhinoceroses dominated the frozen landscapes, but disappeared when the climate warmed again. It was nature once more rebalancing the board of life. The minor extinctions show that Earth never seeks permanence, only movement. It alternates between destruction and creation as if it were breathing. Every loss is also a release, the space needed for something new to emerge. Evolution, in its essence, is a dance between ruin and rebirth. The planet, which has already endured 5 great collapses, continues to perform these small adjustments, reminding us that stability is only a geological illusion. These cycles of cleansing were the prelude to the final transformation, the emergence of a species that, for the first time, would have the power to provoke a global extinction without relying on volcanoes or asteroids. And this new force would not come from the depths of the Earth. It would come from within life itself. For billions of years, the forces that shaped Earth's destiny were natural: fire, ice, impact, and time. No species had ever interfered consciously with the planet's cycles, until one, small and curious, began to transform the environment on a geological scale. That species is us. And for the first time in the history of life, extinction does not come from space or magma. It comes from intelligence itself. Scientists call this new age the Anthropocene, the age of man, a period in which human activity has become comparable to volcanoes, seas, and tectonic plates in its power to alter the planet. Cities spread like artificial rock formations, rivers are diverted, forests are cut down, and entire species vanish at an accelerated pace. Earth, which always renewed itself through natural causes, now faces a transformation driven by its own conscious creation. The 6th mass extinction did not begin with an impact or eruptions. It began with agriculture, with fire and with machines. Less than 10,000 years ago, humanity began a silent process of environmental transformation. Deforestation for cultivation, altered the atmospheric balance. The use of fossil fuels returned to the air the carbon that had been trapped for hundreds of millions of years. The planet, accustomed to slow changes, was suddenly forced to adapt to a new age in just a few generations. The current extinction is unlike any that came before, not only because of its speed, but because of its origin. It is not the result of blind forces. It is the result of choices. The rate of species disappearance today is 1,000 times higher than the natural rate observed in the fossil record. In less than 3 centuries, humanity has transformed the surface of the Earth more than glaciations and cosmic impacts did in the last 100 million years. Ancient forests have been reduced by half. Rivers have been dammed, seas polluted, soils poisoned. Life is retreating, not because the planet demands it, but because humanity does. The Anthropocene is also an age of paradox. While destroying, humanity observes and understands the workings of Earth as never before. Satellites track deforestation, sensors measure the air, and computers simulate possible futures. Science records, with terrifying precision, the collapse it strives to prevent. Knowledge expands at the same pace that biodiversity declines. It is an age of consciousness and of contradiction. Among the most silent victims of the 6th extinction are pollinators, marine species, and soil microorganisms, invisible yet indispensable. Without them, food chains collapse. The fall does not begin with the great creatures, but with the small ones. It is in bees, corals, and bacteria that balance first unravels. When they disappear, everything else follows. Life is a web, and its central thread is being cut. The climate, which once guided Earth's rhythm, now responds unpredictably. Global warming intensifies droughts, storms, and fires. Glaciers melt, raising sea levels. Ecosystems shift, trying to follow the heat. Species migrate to colder regions, but not all succeed. The time of evolution cannot keep pace with the time of machines. And the result is the same as in every one of the 5 previous extinctions, an ecological collapse spreading in chain reaction. Scientists warn that we have already crossed several planetary boundaries. These are invisible frontiers that, once breached, make a return to balance almost impossible. Excess carbon dioxide, deforestation, and ocean acidification are signs that the planet has entered a state of alert. Earth is reacting. Extreme heat, floods, and food crises are not punishments. They are physical consequences of a destabilized system. Yet, even in this scenario, there is resistance. Life insists. In fragmented forests, small species of plants and insects continue to adapt. In polluted seas, new ecosystems are forming around human debris. Nature does not surrender. It reorganizes. The problem is that the natural pace of adaptation is far too slow for the speed of current transformations. What is at stake now is not just the survival of isolated species, it is the stability of the biosphere as a whole. The 6th extinction is the direct reflection of human power, but also the mirror of human responsibility. For the first time, a species understands the impact of its actions and possesses the means to reverse them. There is still time, scientists say, but the ecological clock is ticking. Every decade of inaction equals thousands of years of imbalance. The window for regeneration still exists, but it narrows with every harvest, every fire, every ton of carbon released into the air. The Anthropocene is not only a geological era, it is a moral mirror. It reveals how life has become hostage to a single collective behavior. If humanity chooses to ignore the signs, its fate may echo that of the Permian, the era when Earth nearly died. But if it chooses to understand, act, and restore, the Anthropocene may become the opposite of an extinction, an age of convergence between consciousness and nature. Because perhaps the purpose of human intelligence is not to dominate Earth, but to return it to the balance it has always sought. The planet is on alert. Never before has science witnessed so many changes happening at once. The air, the water, the soil, and the temperatures are shifting at a pace that exceeds life's natural ability to adapt. The numbers are clear, the data consistent, and the conclusion inevitable. Earth is entering a new state. The question is no longer whether the world has changed, it is how much time remains to slow the transformation we ourselves have unleashed. In less than 2 centuries, the concentration of carbon dioxide in the atmosphere has risen more than at any other time in the past 800,000 years. Glaciers that took millennia to form are melting within decades. Entire oceans have changed their chemical composition, becoming more acidic and warmer. An average increase of only a few degrees Celsius is enough to alter ocean currents, shift rain belts, and transform entire ecosystems. The balance that sustained human civilization is trembling before our eyes. Science observes these signs with the precision of a doctor listening to the heartbeat of a patient in crisis. Satellites record polar melting, ocean buoys measure the warming of the seas, and laboratories around the world monitor the gases that trap heat in the atmosphere. Each data point is a line in a planetary medical record, revealing a worrying diagnosis. Earth is feverish. The symptoms are multiple: more intense wildfires, more destructive storms, longer droughts and deadlier heat waves, and all point to the same energetic imbalance. Climate change does not affect only the physical environment. It is redefining the boundaries of human society. Millions of people already live under the threat of water scarcity. Harvests are failing across entire regions. Tropical diseases are spreading into once cold zones. Coastal peoples are losing land to rising seas, and mountain species climb higher until there is no altitude left to survive. The natural world and the human world are intertwined in a crisis that knows no borders. The causes are well known and precisely measured. The burning of fossil fuels, the destruction of tropical forests, the intensive use of land, and large-scale industrial production are the main sources of imbalance. Earth is covered with scars left by progress. Forests turned to pasture, rivers converted into canals, mountains hollowed out to exhaustion. Every material advance of modern civilization carries a biological cost that now accumulates on a global scale. The bill has arrived, and it is expressed in heat, loss of biodiversity, and climate instability. Yet science does not speak only of collapse, it speaks of response. The same tools that reveal the problem also show paths toward regeneration. Clean energy technologies, large-scale reforestation, ecosystem restoration, and new agricultural practices demonstrate that it is possible to reduce pressure on the planet. Research in biology and atmospheric chemistry seeks ways to capture excess carbon and return it to the soil. Scientists, engineers, and environmentalists are working to design a model of survival compatible with the century we live in. The challenge is time. Nature can heal, but it needs space and pause. Humanity, however, still lives at the pace of haste. The decisions we make today will determine the kind of planet that will exist in the centuries to come. What is at stake is not only environmental stability, but the future of all species that share this world. Science has already done its part. It has shown the evidence, projected the scenarios, and pointed to the solutions. The rest depends on the collective will to change. The planet is on alert, but it is not yet condemned. Earth's geological history proves it has always survived, but that does not mean we will survive with it. The difference in this era is that for the first time, there is awareness of the danger and also the power to avoid it. Nature does not need heroes, only balance. And perhaps that is the greatest lesson of modern science. It is not about saving the planet, but about relearning how to live with it. In every collapse throughout Earth's history, death seemed final. Poisoned oceans, skies filled with ash, continents torn apart, and yet something always endured. Life, even reduced to its smallest form, found a way to cross the impossible. Among the billions of species that have emerged and vanished, a few resisted everything. They were shaped by fire, radiation, cold, and absence. They are living witnesses of the planet's deep history, the survivors who defeated time. In the dark, deep seas, where the heat of hydrothermal vents could destroy almost any organism, live bacteria that feed on sulfur and thrive at extremely high temperatures. They are direct descendants of the earliest forms of life on Earth. They existed long before the dinosaurs, and if the planet dies again, they will probably be here after. They are called extremophiles, creatures that make adversity their home. They need neither light nor oxygen. All they require are rock, heat, and patience. Other survivors, visible yet silent, have roamed the surface for millions of years. Crocodiles, descendants of Triassic archosaurs, have survived every major extinction since the age of dinosaurs. They have changed little because they were already perfect at birth. Their bodies are a precise combination of strength, endurance, and efficiency. They can go months without eating, slow their heartbeat, and remain motionless while the world changes around them. They are the portrait of biological persistence. In the depths of the oceans, the coelacanth, a fish once believed extinct since the Cretaceous, was rediscovered alive in 1938. Its anatomy has barely changed in 300 million years. In its fins, it carries the same bone structures that once allowed vertebrates to walk on land. It is a bridge between worlds, a living proof that evolution is not a straight line, but a circle that always returns to its origins. Ferns and horsetails, ancient plants that dominated the swamps of the Carboniferous, still spread spores just as they did before the existence of flowers. They survived glaciations, deserts, and global fires. Their descendants still grow quietly in humid, shaded environments, a reminder that Earth always leaves space for what is simple and efficient. Among the most enigmatic organisms are the tardigrades, tiny eight-legged beings nearly invisible to the naked eye. They withstand temperatures close to absolute zero, pressures greater than those at the ocean floor, and even the vacuum of space. When the environment becomes lethal, they enter total suspension, shutting down metabolism completely. Years, centuries, or perhaps millennia later, they can return to life with a single drop of water. They are the ultimate boundary of biological endurance, creatures that turn death into waiting. There are also sharks as heirs of lineages that appeared before the first terrestrial forests. They have survived glaciations, impacts, and the collapse of their ecosystems. Some species, like the Greenland shark, can live for more than 400 years. Their blood contains compounds that resist extreme temperatures and infections. They are the oldest travelers of the seas, witnesses to a planet that has never ceased to change. The list of survivors also includes invisible organisms that sustain all life above them. Cyanobacteria, responsible for the early oxygenation of the atmosphere, remain present in every lake and every drop of the ocean. They created the air we breathe and have continued the same task for over 3 billion years. In every human breath lies a trace of that ancient and silent labor. But the secret of survival lies not only in physical resistance. It lies in flexibility, in the ability to transform without losing essence. The species that endure are those that adapt, changing behavior, habitat, or form. Nature does not reward strength, but plasticity. Life is not static. It moves among ruins and rebuilds what time destroys. The study of these survivors is a window into the future. If Earth is entering a new age of extinction, understanding who endured before may reveal who can endure again. Each of these beings carries a lesson. Life does not vanish. It reorganizes. Even when everything seems lost, there is always a biological thread that survives, ready to restart the cycle. And perhaps that is the greatest message hidden in geological time, that Earth never gives up. That, after every destruction, it finds a way to be born again, through invisible bacteria, forgotten fish, or small plants that refuse to die. These survivors are the planet's enduring heart. They are living proof that death is never the end, only the pause between two beginnings. Earth's fate is written in the light that warms it. The sun, which made every leaf, every sea, every breath possible, is also the clock that marks the limit of the biosphere. Stars like ours do not burn the same way forever. Slowly, almost imperceptible on a human scale, they become brighter and hotter. In that gradual, patient, inevitable change rests the future of everything living on this planet. The story we've told so far, of 5 deaths and many restarts, was shaped by volcanoes, impacts, and extreme climates. The next great force will not come from Earth. It will come from the sun itself. Over hundreds of millions of years, nuclear fusion in the star's core turns hydrogen into helium. This change in composition alters the internal balance and little by little increases solar luminosity. To us, a harsher summer seems like a quirk of weather. To geology, it is the omen of a new planetary state. A few 100 million years from now, the added energy will evaporate more water, thicken atmospheric humidity, and feed back the warming through water vapor, a powerful greenhouse gas. Rain belts go awry, deserts advance, and the poles cease to be vaults of ice. The pale blues on maps begin to retreat. The first frontier of the end is not fire, it is thirst. When evaporation outpaces the atmosphere's ability to return water to the surface, Earth enters a moist greenhouse regime. The oceans become tanks of steam, the sky a murky, heavy dome. Air chemistry shifts. Photosynthesis, squeezed by heat and water scarcity, stumbles. Forests collapse into mosaics of stressed vegetation, then into clearings, then into dust. The biosphere, which has already survived 5 cataclysms, tries once more to hold the balance. It sacrifices exuberance to preserve only the essential. The planet shrinks biologically, and even so it resists a little longer. On longer timescales, thermal pressure wins. Water vapor rises, is split by radiation, and hydrogen, too light, escapes to space. It is the slow flight of the oceans. The Earth, once oceanic, becomes a world of salt flats, mineral crusts, and desiccated basins. Without liquid water at the surface, photosynthesis finally collapses. Oxygen declines. Higher food webs go extinct. What remains are microorganisms adapted to subterranean niches, porous rocks, films of water trapped in minerals, perhaps fleeting ecosystems beneath twilight surfaces. Life reduces to the plausible minimum and postpones the end. Further on, the star crosses another threshold. The sun, now far brighter, drives Earth toward a Prim's runaway greenhouse. The crust heats, minerals dehydrate, and the very air grows parched. The landscape resembles an open geological archive. Fossilized seafloors, valleys polished by wind, mountains shining beneath a white sky. The planet returns to the mineral silence of its youth. If anything lives, it lives hidden, and not for long. What follows is stellar metamorphosis. When core hydrogen is exhausted, fusion migrates outward, and the sun begins to ice-swell. In the red giant Hutty phase, its radius grows by tens, then hundreds of times. Its brilliance transforms the inner orbits into a furnace. Mercury and Venus vanish. Earth, if not engulfed, is baked to its iron spine. Mountains melt like geologic wax. The mantle bubbles near the planet's skin, and no organic molecule survives. Life's last signatures, thin carbon layers, fossils, biogenic minerals, are remelted in the thermal crucible. Biology becomes physics. The spectacle does not last forever. As the sun loses mass and exhausts its fuel, it sheds a colorful shell of gas, a geoplanetary nebula. At the center remains the exposed core, a geo-white dwarf, the size of Earth with unimaginable density. The light bathing our world is no longer flame, but ember. If Earth still exists, it will orbit as vitrified ruin, a sphere of recrystallized rock, without air, without water, without active history, only memory, mined in silence. In that final interval, the planet does not die, as in our metaphors. It transfers its history. Elements that once made leaves and bones, seas and clouds disperse. Some are blown by the star itself in winds that adorn space. Some stay locked in dense rock. Some, long afterward, may join other dust clouds, other orbits, other worlds. The continuity of matter does not console, but it explains. Earth, which so often rose from its ashes, at last dissolves into them. The ultimate extinction is not an event. It is a trend fulfilled. There is, however, a final layer to acknowledge. Between today and that horizon lie countless biological and cultural decisions. The sun sets the ultimate limit. We decide the path to it. If the 6th extinction is contained, the biosphere will retain diversity longer. If we insist on rapid collapse, we will anticipate the aridity the star would only demand in ages to come. The future far from the sun is not just a distant image. It is the mirror reminding us that cosmic time is immense, but the useful time of complex life is finite and precious. When the light becomes ember and Earth becomes memory, the universe will not know our names, but it will keep in minerals and chemical traces proof that here there were seas that sang, forests that breathed, and minds that understood. Until then, this world is still blue, it still rains, it still blooms. And while it is so, what we learned from the 5 deaths and from the 6th tomorrow should guide every act. Prolong the habitable window, protect what remains, and restore balance to the system that sustains us. One day, the sun will fail us. Until then, let us not fail our judgment. Life never gives up. Even after the greatest catastrophes, when the planet seems empty and silence rules the seas and mountains, it always returns. It may take millions of years, it may change its form, but it comes back. This is the most constant law in Earth's history. Nothing living disappears completely. It only transforms. Life is not fragile, it is patient, and time is its most faithful ally. After every mass extinction, Earth became a laboratory of restarts. When the Ordovician ice melted, the seas began to pulse again. After the Devonian collapse, new forms of plants conquered dry land. The inferno of the Permian gave rise to the reptiles that would dominate the planet. The Triassic chaos paved the way for dinosaurs, and the Cretaceous impact opened space for mammals. Each end was also the beginning of something new. On Earth, death is the mechanism of rebirth. The rocks tell this story in layers. Each stratum of sediment holds not only ashes and fossils, but also signs of adaptation. New forms of life appear just above the destruction of the old ones. It is as if the planet breathes, inhaling creation, exhaling extinction. Geology itself is the physical testimony of biological persistence. What changes are the shapes, the faces of life, but the vital impulse that never ceased. Scientists call this pattern evolutionary radiation. After every extinction, biodiversity bursts into new directions. Small, discrete species occupy the spaces left by vanished giants. Nature uses emptiness to experiment. Biological creativity is born from absence. Life blooms in the ruins. It has always been so, and perhaps it will remain so until the planet's final day. The force behind this return is written within the molecules themselves. DNA is a library of survival. It carries records of millions of trials and errors, adjusting with each generation. It is a planetary archive of memory, continuously rewritten. When the environment changes, genes change with it. When the planet grows ill, life learns to heal it. Earth and the living beings form a single organism, interconnected and self-regulating, in a constant attempt at balance. The history of extinctions is, therefore, the history of rebirth. No event, however devastating, has ever erased the impulse to exist. Even extinctions that wiped out 90% of life left enough for a new beginning. A single cell, a single resistant organism, can rekindle the flame of the biosphere. Earth knows how to rebuild itself, and it does so with an elegance no catastrophe can interrupt. The idea of an eternal return of life is not philosophy, it is geology. It is written in fossils and carbon cycles, in climate oscillations, and in forms that reappear after chaos. With every extinction, nature redefines what it means to be alive. Ancient creatures vanish, but their structures return in new versions. The flight of birds was born from the leap of reptiles. Mammals came from the shadows left by dinosaurs. Innovation is nature's natural answer to destruction. Today, as we face the sixth extinction, that same force still acts. Humanity witnesses the accelerated loss of species, yet also the creation of others. In cities, new ecosystems emerge. Insects adapt to concrete, plants grow in cracks, animals learn to coexist with human noise. Life does not need permission to continue. It infiltrates, multiplies, and silently turns chaos into opportunity. Even when nature appears devastated, the restart is already underway. Seeds sleep for centuries, waiting for rain to return. Spores travel on the wind until they find fertile soil. Bacteria survive in ice and awaken when warmth returns. Life is always waiting, ready to reclaim the world. This invisible persistence is the true engine of Earth. Every great extinction was a pause, not an end. Earth is the stage of an unending drama, where the plot repeats but the characters change. In each act, new forms of life arise, performing the same universal role, to exist despite everything. And in this continuous motion of death and rebirth, Earth finds its balance, because to live at its core is to learn how to begin again, and as long as there is a fragment of light, a molecule of water, a spark of energy, there will also be the return of life. Earth's history is at once a tragedy and a promise. In its 4.5 billion years, it has died many times. It has been covered by ice, set ablaze by volcanoes, struck by asteroids, and suffocated by toxic gases. And yet, it survived. 5 times life nearly vanished. 5 times it returned. And now, in the face of a new crisis, the planet watches us again, waiting to see what role humanity will choose in this 6th era. Each extinction was a warning. The Ordovician taught that cold can paralyze the ocean. The Devonian showed that green can also suffocate. The Permian proved that fire can burn even the air. The Triassic and the Jurassic reminded us that chaos can make room for creation. And the Cretaceous revealed that even the greatest beings can fall in the blink of an eye. No age was eternal. No dominion lasted forever. Earth does not belong to those who live on it. It belongs to time. Today, time has become conscious. We are the first species capable of understanding what is happening as it happens. Science is the mirror of that awareness. It records, analyzes, and predicts. But understanding is not the same as acting. Knowing that an extinction is underway is not enough to stop it. What humanity lacks is not knowledge, and it is responsibility. And perhaps that is what the Anthropocene is trying to teach, that power without care is just another form of destruction. The lesson of the 5 deaths is simple and final. The planet recovers, but life never returns the same. When a balance is broken, it takes millions of years to reform. Every species lost is a library erased, a genetic code that cannot be rewritten. If humanity continues to act as a force of extinction, the future may remember us as just another layer of fossils, filed among the eras of destruction. But if it chooses the path of preservation, it may become the first species to understand and halt a global catastrophe before it completes itself. Earth does not need to be saved. It needs to be respected. The planet has already survived worse disasters than us. The real risk is not the end of the world, but the end of our place in it. Life will go on in one form or another. What is at stake is whether we will be part of it. This is the 6th choice, the one that can still be written. While the ice melts, while the forests breathe, while the seeds germinate, Earth is still trying to teach us. The same force that allowed life to return after every catastrophe continues to act now. It is up to us to decide whether we will be its continuation or its obstacle. Because if there is one truth that runs through all ages, it is this: life always finds a way, but it does not always find it with us. The story of the 5 great extinctions is the story of a planet that never gave up. And perhaps by understanding this, humanity will finally learn to remain. Earth is ancient, patient, and just. It gives back everything, what it receives and what it loses. And in the end, when the sound of civilization falls silent, it will be the same sound as always that fills the air, the wind, the rain, the distant song of the creatures that endure. The planet will go on, as it always has. And so the journey comes to an end. The Earth, which has died and been reborn so many times, keeps turning in silence beneath the same sun that will one day watch it sleep. Each extinction was a pause, each rebirth a chance. And as long as there is light, the cycle will continue. Because life, in all its forms, in all its times, never forgets the way back. Close your eyes. Imagine the ancient seas, the ancient winds, the forests that once covered the world. They are still here, in fragments, in seeds, in memories kept within stone and water. The planet breathes slowly, but it still breathes. Thank you for joining this journey through the deep history of the Earth. If this story touched you in any way, like this video, subscribe to the channel, and comment where you are listening from. In doing so, we keep alive curiosity, science, and love for our small blue world, the only one we know and the only one that insists on beginning again, despite all the threats of the universe and great extinctions. Sweet dreams, and see you in the next video.